we started off the unit and discussed the introductory part of the induction motor, the three-phase induction motor. And one of the things we discovered is that three-phase windings can produce a revolving magnetic field even while they are stationary. So in our lesson today, we'll continue from where we stopped. Though perform some small recap. So we considered such a machine that had the three-phase windings are set, and we discovered that if we allow the currents to flow as indicated, that there'll be a revolving magnetic field created in those three-phase windings that will revolve as indicated at an angular velocity omega. That angular velocity will later become what we know as the synchronous speed. Then we also raised mathematically that the magnetic field can be represented in form of a cosine wave as indicated. And we established the equation and consequently the flux per pole. Now, if we recall from physics, the EMF induced is proportional to the rate at which the flux is changing. And considering the flux linkage as lambda A, then the flux linkage can be in form of an equation written as n phi p cosine of omega t, where phi p is the flux per pole. And consequently, from Faraday's law of electromagnetic induction, we established that the EMF induced per pole or per coil will be the rate at which the flux linking is changing. And the same equation will apply for phases B and C, only that phases B and C will be out of phase by 120 degrees, either plus or minus. Then next, when we divide the EMF induced by √2, we get the RMS value of that EMF, and we get an equation that we are familiar with, the general transformer equation. And this is where we established that an induction machine is actually a revolving transformer because the principle of operation of a transformer was based on the fact that the secondary side and the primary side are not electrically connected, they are linked magnetically. And that is the same consideration we have for the induction motor. The primary side, which is the stator, and the secondary side, which is the rotor, have no electrical connection. They are purely a magnetic linkage. And that's why this formula comes into play. 4.44 F, which is the frequency, number of turns, and the flux per pole. So the only adjustment we do for the induction machine is we add a factor kW. Now, the rotor speed and the slip. Having established that we have a revolving magnetic field in the rotor, in the stationary stator windings, and we also established that if we have a magnetic field moving in a particular direction and cutting stationary conductors, then the conductors will experience a force which we call the Lorentz force, and will tend to move the conductors in the same direction as the moving pole. So the same concept now is adopted here in the induction motor. So we have the revolving magnetic field, and we have the stationary rotor conductors. So once this revolving magnetic field cuts the stationary rotor conductors, an EMF is induced in that particular conductor. And since that conductor is under a revolving field, then that conductor experiences a force known as the Lorentz force, which will cause the rotor to move in the same direction as the revolving magnetic field. And the rotor will move at a speed slightly less than the speed of the revolving magnetic field. And that's why we call it an asynchronous machine. Asynchronous to negate that it does not revolve at synchronous speed. So that's what is explained here. Now, the difference between the speed of the starter field or the synchronous speed and the rotor speed is known as the slip and is usually expressed as a percentage, so or decimal. So ns minus nr over an s, and this is a parameter given for a particular machine. So when you have the nameplate readings of a machine, one of the parameters given is the operating slip or the rated slip. Now, since both the revolving magnetic field and the rotor are moving in the same direction, then the relative speed between them is reduced. It is actually ns minus the speed of the rotor, n. Consequently, the frequency in the rotor will also be reduced because it will be a factor of the slip. And consequently, F2, which is the slip of the rotor side, known as the slip frequency, will be the slip multiplied by the frequency of the starter side. This also affects the EMF. When the rotor was standstill, it induced maximum EMF on the rotor side. But once the rotor starts to rotate in the same direction as the revolving magnetic field, then the EMF on the rotor side reduces by a factor of the slip. And that's why we say E to S is equals to the slip multiplied by E2, where E2 is the induced voltage when the rotor is at standstill. And then the speed of the rotor will also be a factor less than the and consequently we can write it as SNS. So these are very key for us to understand. And let's see whether we can solve this question. I'll give us a 2-minute silent time to try and go through the question. A 3-phase 460 volt, 100 horsepower, 60 hertz, 4-pole induction machine delivers rated output volt power at slip of 0.5. Determine the synchronous speed and motor speed, the speed of the rotating air gap field, the frequency of the rotor circuit, the slip RPM, the speed of the rotor field relative to A, rotor structure, B, starter structure, and 3, starter rotating field. And F, the rotor induced voltage at operating speed if the starter to rotor ratio is 1:0.5. So let us have 5 minutes to think how we can solve that, and then we look at the solution together. So let's understand the question. So we have a 3-phase 460 volts, 100 horsepower, 60 hertz, 4-pole induction machine delivering at rated power and a slip of 0.5. So first of all, what will be the synchronous speed and what will be the motor speed? So in this case, motor speed also is the rotor speed, the actual speed at which the rotor is rotating. So we have seen that the synchronous speed and the rotor speed are different by the factor of the slip. And the synchronous speed can be calculated as 120 F over P, and the motor speed can be now that speed minus the slip speed, or you can do NR is equals to NS1 minus S in brackets. So I'll also present the solution. What will be the speed of the rotating air gap field? So we have already seen that, discussed actually, that the air gap field is the one which actually rotates at synchronous speed. What will be the frequency on the rotor circuit? Now, when you look at the rotor and the stator field, you should look at it as two cars moving in the same direction, but one car is slightly faster than the other. Consequently, the slip at the frequency of the rotor will be much less than the frequency of the stator side. And to get the frequency of the rotor, we will multiply the frequency of the stator side times the slip, and that is the relative speed between the two machines, two moving parts, the revolving magnetic field and the rotating rotor. The slip RPM is now the difference between the two speeds, the synchronous speed and the motor speed. And then part E now is having understood what is happening in the stator side and in the rotor side, then we are able to judge part E. What is the speed of the rotor field relative to the rotor structure? So remember, there's a field rotating, and the stator structure, the rotor structure is also rotating. So what will be the relative speed between the two? I would want you to think about it. Now, the field in the rotor is revolving. The stator structure is stationary. So what should be the relative speed? And then the field in the rotor is revolving and the field in the stator is revolving. So part 3, what is the relative speed between the two? And then finally for part F, the induction voltage, the induced voltage, the rotor induced voltage at operating speed, if the stator to rotor turns ratio is 1:0.5. So remember, we have said we can view the induction motor as a transformer. So if the rotor was standstill, if the voltage on the stator side was 1, then the voltage on the rotor side will be 0.5 volts. What if the machine is revolving? What will be the difference? The difference, the turns ratio will remain the same, only that now the rotor induced voltage will reduce by a factor of the slip S. So we can now view the solution together. So the first part is 120F over P, and we now can see the speed will be 1,800 RPM, and consequently the motor or rotor speed will be a slip less than that, which is 1710 RPM. Then part B, what is the speed of the revolving field? It will be the same as the synchronous speed. Then part C, what is the frequency on the rotor circuit? The frequency of the rotor circuit is a slip, is a factor of the slip, so it's 0.5 of 60, which is 3 hertz. And then what is the slip RPM? Yeah, slip RPM, you can either multiply S multiplied by 1800, which is the synchronous speed, or you subtract the synchronously revolving field, 1800 minus 1710, you get 90. Now, here is where we were talking of the relative speed. So here it is 90. Now you'll relate to the question. I can't recall how it is phrased. Here it is 1800 relative speed. This was the starter structure, if I'm not wrong. So since the starter structure is not revolving, then the relative speed will be 1800. And here the starter rotating field and the rotor field are the same. So the speed difference is 0. And then finally, the induced voltage on the rotor side. So remember, I mentioned that if the stator and the rotor were not revolving, the turns ratio will be N2 over N1. So if N1 was 1, and if N1 was 1, then we can get N2 as 0.5. However, since the rotor is rotating, we now multiply the entire turns ratio by S. So this is the new aspect indicating that the voltage will now be much reduced because the machine is rotating, and you get 6.64 volts. So that's how to solve that simple question. Now, next we can move to the equivalent circuit. What is the equivalent circuit of an induction machine? For us to capture the induction machine, again, we bring the concept of the conventional transformer. Now, the conventional transformer has two parts. Has the primary side, which is the receiving end. So in our case, it will be the starter. And then has the secondary side, which is the secondary side is the rotor. The primary side is the starter. And in between the starter and the rotor is a magnetic linkage. So in the case of the transformer, the magnetic linkage is a magnetic circuit formed by steel alloys. But in the case of the induction machine, it's an air gap. It's an air gap. However, it is a small air gap. So this is how the induction machine would look like at standstill. Now, in the case of the transformer, if you recall transformer theory, the exciting current was much smaller compared to the load current. It was actually 1 to 5%. So in some cases, we would neglect it to come up with what we call the series model of the transformer. However, this is not the case when we come to the motor. The exciting current can be as high as 40% because of the air gap. Consequently, the magnetizing branch is key in induction machines, while in transformers, it is negligible and often is ignored in some calculations. So the other major difference is that induction machines have a higher reactance, X1, due to the air gap, and also because the starter and rotor windings are distributed along the periphery of the air gap rather than concentrated in the core, as in the case of the transformer. So those are two major differences in modeling. However, the basic model remains the same. We have the starter, we have the magnetizing branch, and then we have the rotor side. Now, the other thing to consider is the magnetizing branch. And usually in the magnetizing branch, for the case of the induction machine, we will remove RC, which accounts for the core losses, and instead lump them as core losses when we are dealing with the mechanical losses. So that's an additional adjustment when modeling. Now, the rotor circuit is interesting because the current in the rotor circuit is only limited by the impedance in the rotor circuit, or I2 is equals to SE2 over R2 JS X2. And that circuit would look like, is actually this one. And the power associated with this circuit, as from circuit theory, will be I squared R2. Now, this circuit we say is at frequency F2. However, if we do a slight manipulation by taking equation A and dividing the numerator and denominator by S, we come up with a new equation. I2 remains the same. However, because of dividing the numerator and denominator by S, we end up changing the frequency. So we are no longer at frequency F2, but we are now at supply frequency F1. And the circuit would look like this. And the circuit that relates to this now is at supply frequency. This one was at rotor frequency. So that's a key difference in modeling, and it has its own implications, which are narrated in the following slide. So although the magnitude of the current in both equation A and B are the same, the two equations are significantly different. The two circuits are significantly different. The first circuit was at sleep frequency F2, whereas the second circuit is at line frequency F1. Equation A, represented by circuit B, is the X2 is a variable, whereas the R2 is constant. Equation B, relating to our diagram C, X2 is now constant, but the resistance is a variable. And since we are dividing the resistance by a small value of the sleep, then the power associated with this circuit is I2 squared R2 over S. Since we are dividing by a small value, we end up having a very big power associated with this circuit. It's actually the initial power divided by S. So again, since we are dividing by a fraction, then this represents a bigger value. It is actually known as the air gap power. That is the power that is transferred from the primary side, which is the starter, crosses the air gap into the rotor. So in terms of the total equation now, PAG, the air gap power, can also be expanded in this format. When it's expanded in this format, then the first portion represents the power loss, and then the second portion represents the power that is actually going to be developed. So far, this is the model we have. We have been able to bring this part of the circuit to supply frequency, and hence now bring it together with this. So if you recall from your knowledge of transformer theory, here is a magnetic linkage that needs to be gotten rid of. So that's the first thing we get rid of by scaling the transformers, that is referring the secondary parameters to the primary side or the primary parameters to the secondary side. So in this case, we are referring the rotor parameters to the starter side. That's why we have A, where A is the transformation ratio. So the other thing that is done is to get rid of RC, which we'll be doing shortly. So in summary, this is what we have so far. The developed power is given by that, or 1 minus S of the air gap power. The air gap power, remember, is the power that is shifting from the starter to the rotor side. And then the power available to be developed is as indicated, and consequently, we now can get the ratio between the air gap power, the losses, and the developed power as 1 is to S is to 1 minus S. So what will be the recommended IEEE equivalent circuit? As you well know, IEEE is an association that electrical engineers join to do research, and they come up with different standards for modeling and calculating of many aspects in electrical engineering. So in terms of the equivalent circuit, they recommend that RC to be omitted and to be lumped in form of windage and friction losses. So that means this is removed. So once that is removed, we now have what we call the IEEE recommended circuit. So this circuit is fairly accurate in all calculations involving three-phase induction machines. So, and generally the power flow will be as follows: power input from the starter, Part of it is lost in the starter as starter copper losses. Whatever remains is what we are calling the air gap power. It crosses from the starter side to the rotor side. Part of it is lost as copper losses in the rotor windings, and whatever remains is the developed power. If we now know windage, friction losses, we subtract from the developed power and we get what we call the shaft power or the output power of the induction machine. Good. Then we can talk about the Thevenin circuit, but I would have hoped we have an example first. So let us look at this example first, then we will come back to Thevenin's theorem. So again, I give you 2 minutes to complete the question before share it. So let's go through the question. So we have a three-phase 280 volt, 60 hertz, 20 horsepower, 4-pole induction motor with the following equivalent circuit parameters. So we have R1 given, R2, X1 equals to X2, and XM. The rotational losses are given. The slip is given. So the question is, what is the motor speed in RPM and radius per second? Motor speed, starter copper loss, air gap power, rotor copper loss, and shaft power. So the first and foremost is to be able to have the circuit diagram. So again, we use the recommended IEEE circuit. So, and we have all our parameters put in place. So if we have them put in place, then you'll notice first of all that the synchronous speed is still the same, 120 F over P, so we get 1800. Then we can change 1800 revolutions per minute to radians per second. So you multiply by 2 pi and divide by 60 to get the speed in radians per second. So the rest is generally circuit theory. So we have our R1 and X1, we have our X2, we have our R2 as R2 divided by the slip, so we get 2 ohms, and we have our XM. So first we can get Z1 or Z total, which will be now this plus this parallel to this as indicated. So once we have the EMF, the impedance, and we know the voltage, remember this is a 3-phase machine, so 208 over root 3 to change to phase voltage. So this over this should be, so usually there's a mistake here, this should be 56.3494, and this angle. So then part 1, we can get the power associated with the starter losses as the current squared multiplied by the resistance, and since there are 3 phases, we multiply by 3, so we get 11.43.03. Then next is to get the power associated on the starter side. So how much power is being generated on the starter side? It is 3 multiplied by the phase voltage, the current, and the power factor, and we get 18,610.9794 watts. So the air gap power, that is the power that will cross from the starter to the rotor, must be what is generated in the starter minus what is lost in the starter. So we get this. So once we have the air gap power, we can get the losses in the rotor side as the slip multiplied by the air gap power, and we can get the developed power as 1 minus S of the air gap power. So that's how to quickly solve this question. So I want to quickly go through the Thevenin's theorem and its application in the motor as we conclude for today. So go back 2 steps. So sometimes we need to simplify the circuit model, or any circuit model for that matter, so as to be able to solve and get other parameters in a much easier way. So Thevenin's theorem becomes, again, very handy. If you recall Thevenin's theorem, it states that if you have a 2-port system, or if you can identify 2 ports in a network, then those 2 ports can be reduced to a voltage equal to the open circuit voltage as viewed from those 2 ports, and an impedance equal to the impedance as viewed from those 2 ports when all sources have been removed and replaced by their internal resistances. So that's exactly what we do here. So we are viewing, we want to, for example, Devenize the starter side. So we view from the rotor side. So if we view from the rotor side, the voltage that will be the open circuit voltage can be given by Xm over this times V1. And this you can easily see from, you can use what we call the voltage divide rule and to establish the same. And since R1 squared is much less than X1 plus Xm squared in this equation here, then it is possible to approximate the value of the Thevenin voltage as this. And then the Thevenin resistance, again, if you view from this side, then it will be Xm is parallel to R and X1. So, and this gives the Thevenin resistance. So again, since R1 squared is less than this, then the Thevenin resistance can be reduced to this. So, and consequently, the Thevenized circuit of the induction motor can be viewed as this. So this will be used later on as we look at torque relationships in the induction machine. So I'd like to have questions asked. I saw some questions there. The network today is poor. I think it has been poor generally everywhere. Mine is also not doing well. And then number 2, there's still somebody asking about notes, and I thought we already solved that. Everybody can access the notes through the portal. Why we insist in the portal, I want you to get used to it, so that when we start posting even assignments, we'll require you to return the assignments through the portal. And it will help us track how much online our students are. So please sign in for today by clicking the link and filling the guided questions. Once the class is through, I'll also upload the video of the lesson again inside the portal. I hope it will not be too big to be uploaded there. Good. So we'll move on. So tests to determine the equivalent circuit. So I'll introduce the tests today, and then we'll also go through them again as we look at a question in our next meeting. So usually there are many tests done in an induction machine, but the tests we talk about, especially in relation to the induction motor, will be the tests that are used to determine the parameters of the same machine. So for the induction motor, there are 2 tests that are key to determine the parameters. Almost the same way as we did for transformers. There were 2 tests to determine the parameters of a transformer. So in the case of the induction machine, we have the no-load test and the on-load test, and the locked rotor test. No-load test and the locked rotor test. The setup for both tests is the same, in that we measure, one, the line-to-line voltage, two, the power, and three, the line current. In the case of the no-load test, we also measure the line-to-line resistance so as to determine the resistance of the windings. So for the no-load test, what will be the circuit associated with the no-load test? Now, in the no-load test, the slip is exceedingly small. So since the slip is exceedingly small, R2 over S is very high. So in other words, we will be neglecting a certain branch. And if we neglect a certain branch, so this is the equivalent circuit when we are doing the no-load test. So from this knowledge now, and from the tests, this is what we are able to measure. Number one, we are able to measure the line-to-line resistance, and if we divide by 2, we get the rotor starter resistance R1. Then in the no-load test, we measure the line-to-line voltage, we measure the no-load current, and we measure the total three-phase active power. Since we are not measuring X1, but we can determine the no-load reactance, which is X1 plus XM from the following equations. First of all, we can get the phase voltage from the measurement divided by √3. We can get the no-load impedance from the two measurements, voltage and current. Then we can get the no-load resistance from the power divided by 3I squared. And from there, we can get the no-load reactance. And from the recommended IEEE circuit, we assume that X1 plus XM is equals to the no-load reactance XM no-load. The other test that is key is the locked rotor test. So in this case, we hold the rotor at stationary so that it does not rotate. So if we hold the rotor stationary so that it does not rotate, the slip is equals to 1, and the circuit becomes as indicated. Since the magnetizing branch in this case will be much greater than X1, X2, and R2, then it is neglected. So based on this and on the measurements we do, so first of all, we reduce the three-phase voltage gradually. We reduce the three-phase voltage, yes, and gradually increase it until the starter current is about equal to the rated voltage. Sometimes it's recommended to use even lower frequency to avoid what we call the skin effect. So then again, we take the same readings, the line-to-line voltage, the line current, and the three-phase power. So again, based from the measurement of the power, we get the rotor, the blocked rotor resistance. From the measurement of the voltage and the current, we get the impedance. And from the two, we get the reactance. In case we had adjusted the frequency, we immediately correct for that to get the correct reactance of that machine. And then from there, the blocked rotor reactance is assumed to be X1 plus X2. And in a properly designed machine, X1 and X2 are equal. And consequently, we can get X1. And from our previous test, we can now derive XM as X no load minus X1. Now, in the rotor, in the motor, R2 is very important. So R2 can be corrected or improved by, again, applying Devenine technique. Now, in this case, we are viewing from the starter side and seeing what is happening. So from the starter side, this is R and X Devenized would look like that. And the equation now is as indicated, R will be equals to this value. And if X2 prime plus XM is much greater than R2, as is usually the case, then R2 can be estimated from this value. and now R1 is RBL minus R1. So this is very important because R2 is very significant when it comes to induction machines. Good. So we have a question here, which we will consider the solution next time. We'll consider the solution next time, but in your notes it will be clear, though the solution will be covered. So with that, I would propose that we stop there. And if we have any questions, you can raise. I saw somebody type a few issues that they are still not able to access the notes. I will find out why that is the case, because I already uploaded the notes, and then I will give feedback in the group. If they are totally inaccessible, I'll also find a solution to that. But I plan to use the portal to share all the notes and also the videos that are coming out of our discussions here.